Hello friends, so in this video I will talk about the Big Bang Theory, QGP and QCD phase diagram. So QGP stands for Quark Gluon Plasma. So I will explain these terms in a very simple way and the importance also. So in the normal world we see many things. These things are made up of atoms. If you just go see the smallest part is the atom, and inside the atom we have again nucleus and then the electron surrounding the nucleus. So if you go to the electron size is basically less than 10 to the power minus 16 centimeter, less than, and then if you convert into the meter, it's less than 10 to the power minus 18 meter. And the size of the atom is basically typically is 1 angstrom. If you just convert into the angstrom, 10 to the power minus 10 meter. And inside the atom we have again the nucleus. So nucleus, then inside the nucleus, as we know, we have the protons and neutrons, and the size is typically 1 Fermi meter. If you just convert in 10 to the power minus 15 meter. Now inside protons and neutrons again we have the quarks. These are made up of 3 quarks because these are the baryons made up of 3 quarks. The size is again less than 10 to the power minus 18 meter. So if you see the proton, this is made up of 3 quarks, basically 2 up quark and 1 down quark, and these are bind by the strong interactions, which is dominated by the gluons, which is basically they are basically bind by the interactions. So this interaction is exchanged by the gluons. This is the mediator. Like for example, if you have 2 charges, we have the Coulombian interaction. This is basically created by the photons, exchange of the photon, that creates the interaction. Similarly, in the case of the quark, the strong interaction basically is dominated by this exchange of the gluons. So this is created by the exchange of the gluons. So any interaction we have always a carrier. For example, also gravitational interactions, basically we call it it's created by the graviton. So whenever we have 2 mass objects, they attract each other, so there should be some carrier for that, so that is graviton. So in the case of electromagnetic interaction it is photon, and in the case of strong interaction it's gluon. So these are the these interact with each other by the gluons. So we have the 6 types of quarks. Up, U stands for up, and D stands for down, and C, charge, strange, top, bottom. And if you just see this has the largest mass, like 171.2 GeV. So it is given the mass, and charge is basically 2 by 3 of electrons, and the spin is 1 by 2, and you can just see the others the mass and charge and spin and the name also. So these 6 types of quarks we have. So inside the proton we have the 2 up quark and 1 down quark. If you just sum the charge of the 2 up quark, basically 2 multiplied by 2 by 3, that means 4 by 3, and 1 down quark minus 1 by 3, so it basically it gives the charge as 1. And if you consider for the neutron, then we have the 1 up quark, so the charge is basically up quark is 2 by 3, and we have the 2 down quarks, so basically minus 1 by 3 and multiplied by 2. So then if you just sum the charge, overall charge is 0, as we already know that neutrons have the 0 charge and the protons has a 1 charge. So now in this particular scenario we have 2 special properties of these basically bindings of the quark. One is the quark confinement. This is the special features of the quark. Basically, one is the quark confinement, another is the asymptotic freedom. So quark confinement says that individual quark doesn't exist at in the normal conditions. Like for example, if we have up and down quark, if I want to separate up quark, if I pull this quark to separate it, basically I have to supply the energy, then it will not be separated. At some point you can stretch it and it will break, and then this particular up quark, if you just pull them from this, then it will create a new baryon and one quark and anti-quark pair. So that means a quark in the normal conditions, it doesn't exist, individual quark doesn't exist. This is known as the quark confinement. Another feature is the asymptotic freedom. If you go at very high energy, or you just move these quark very close to each other, then their interaction reduces, and they behaves like almost free. This is known as the asymptotic freedom. So at the very high energy limit, they are almost free. Coupling, basically the interaction between them decreases, so that is known as the asymptotic freedom. So in the normal nuclear method, in the case of protons or neutrons, we have the three quarks and they are connected by the exchange of the gluons. So that binds them inside the, let's say, inside the proton or neutron. This is the case of the normal method. And if you go at the level of asymptotic freedom, and let's say in the extreme high energy limits, when then quarks and gluons coupling reduces, at some point they becomes free. So there's a mixture. We can define a mixture where quark and gluons are in the free state. It is known as the Quark Gluon Plasma. Now I will explain the importance of the Quark Gluon Plasma. What is the importance, why it is very relevant for our physics studies. So let's say if I ask very simple questions, how universe is created. So at present what we can see, we have trees, we have a home, we have car, we have everything. But if I ask a very simple questions, how universe is created, how these things looks like 14 billion years ago, or how these things are created at the beginning, then there is a theory known as Big Bang theory that says that initially there was nothing, we have just a singularity, and suddenly Big Bang happened, and then there's a very big bang. So it's kind of a big blast. It's not the normal blast, it's very big. I cannot imagine, because it has created the whole universe. Everything you see, it's because of that blast. So after 1 microsecond of this blast, there's a medium created. It's known as Quark Gluon Plasma, as I mentioned here. So quark and gluons are in free state. So, and the temperature is larger than 10 to the power 12 Kelvin. It's after just 1 microsecond. Now it will cool over the time. If anything is hot, it will cool over the time. So as you can see, now temperature reduces 10 to the power 12 K. And now quark and gluons, if combined, then they will either form protons, or let's say either baryon or meson. If two quarks combine, they are known as the meson. If the three quarks combine, then they are known as baryons. So now quarks and gluons here in the free state, now they will start combining. That will make either, let's say, baryon or let's say meson. So here they say that the protons and neutrons formation take place, and then after that Now protons and neutrons will combine, and that makes the, basically if you combine proton and neutrons, then it becomes basically nucleus, and they forms a low mass nuclei. And then if you just see, then after the nuclei, it will form an atom. Then they will form the, let's say, neutral atoms, and the temperature is decreasing, and then there is star formation, and then the dispersion of massive elements, and then we see the today's life. So this is the theory. It says that initially there are nothing, and how the today's we see the today's situation, and this is the at the beginning, and what are the intermediate step happens in between. This tells about the intermediate step. Now this is a theory. We have to prove whether this medium is created or not, or once if this medium is created, how this medium is, from this medium, let's say quark and gluons in the free state, how this proton and neutron formed, and for example baryon or meson formed, and how from this baryon and meson these atoms form. These all things we try to investigate in the LHC. So what we do there, we collide heavy ions, lead at the LHC, or gold at the REAK at almost speed of light. So we collide them at a point, so it should create like a big bang like situations where we have a very high energy concentrated at a point. And then over the time we found a medium similar to quark gluon plasma, and we examine the properties which basically matches with the quark gluon plasma. Then we also try to study how this quark gluon plasma, how this after this, how it converts to proton and neutrons, how hadronization mechanism, basically in that terms we called it hadronization mechanism. So what are the hadronization mechanism leading to conversion from quark to hadrons, and so these kind of studies we do in the LHC, Large Hadron Collider, basically detection of the quark gluon plasma, which is the one of the key component for the Big Bang theory. So if we detect these all steps, that means this theory is correct. So we study the quark gluon plasma, and then we found we found some of the properties of the medium created which matches with the quark gluon plasma. So this also complements the theory that according to the theory there should be some QCP, and then it should be hadronized, and then it should form low mass nuclei. And these all the steps we try to recover in the experiment by colliding lead nuclei or gold nuclei. Now I will explain about the QCD phase diagram. Now we learned that there are two phases. One is with the normal method where we have proton and neutron. Another phase is QGP phase. This is quark gluon plasma, and then this is the proton and neutron. Now how this transition from quark gluon plasma to the normal method like hadron gas take place, this is what we study in the QCD phase diagram. So it's a phase diagram between the baryon chemical potential. It is expressed in terms of mu b. It is known as mu b, and then the temperature. So we have a parameterization I taken from this paper. This is very well known paper. So if you can see that these are the already given, D and E is already given because parameterized. So if you go infinite energy, this is the energy, so then your mu b is 0. So your Big Bang happened basically at a very large energy, because this has created all the universe. So your mu b is exactly 0. So this is the situation of early universe where mu b is 0. However, the LHC experiments, we have the collision energy of tera electron volt, TeV. so it lies with larger mu b, because if you reduce energy, then you are moving towards this position, and if you further reduce energy, you can move to the higher mu b region. And then the temperature is, this is the another axis is the temperature. So now this phase is the quark gluon plasma at a very high temperature, and so you can just see, and so now our motive is that how this quark gluon plasma is converted into the proton and this hadron gas. Basically we call it hadron gas. Is it a smooth transition or a first order phase transition? For this, theoretical model suggests that in the low mu b region it's a crossover, and higher mu b region there is a first order phase transition. The theoretical model predicts that. So in the higher mu b region we have a first order phase transition, and the low mu b region there is a crossover. We do using the lattice QCD calculation at the low mu b region, and while others region we use the different model to predict what kind of transition it is expected basically. So we have a first order phase transition and then the crossover. The end point of a first order phase transition from the basic thermodynamics is always a critical point. So we are searching for this critical point from the basic thermodynamics. Let's say whenever first order phase transition ends, the line ends, we have a critical point. So this particular point we are searching for in the experiments. So in the critical point, and then the next thing here also we have a first order phase transition, and this lines end somewhere here also, because line will end at some point. So before that at the end point of this there also can be a critical point, because according to the thermodynamics, if it follows the law of thermodynamics, then we will have one critical point. So we are searching these regions. We are looking for the in the experiment what are the signatures we can study for the first for the phase transition. So basically we use the V1 to probe the first order phase transitions, and for the crossover and these regions critical point we use the higher moment analysis of the net baryon, net charge and net strangeness. These all things we study to probe this. Now what is the importance, why we are studying this QCD phase diagram? This is very interesting question. So why we are investigating this? So to answer these questions I will give one logic. So if you want to convert 0 degrees Celsius to 100 degrees Celsius, then how much energy you have to give? Basically Q, MC and delta T. This, if you want to convert 0 degrees Celsius to, let's say 0 degrees Celsius to 100 degrees Celsius water, then we have to give this much amount of energy. And if you do the experiment at the level of water, you just convert 0 degrees Celsius to 100 degrees Celsius, and if you do the theoretical calculation, both will match. But when if I say if you just want to convert 0 degrees Celsius water to 100 degrees Celsius steam, now it's not a water, it's the steam. Then if you use this same formula, let's say if you are using Q is equals to MC delta T, M is the mass and C is the specific heat and TT, then if you, since this is a process you can do experimentally, and if you use this theoretical calculation, this will not match with that. So that means there is some extra process happen here at a constant temperature. So there are basically two processes, 0 degrees Celsius to 100 degrees Celsius water and then 100 degrees Celsius to 100 degrees Celsius steam. So there are two processes, one in which temperature difference take place, another process where temperature of is constant, like 100 degrees Celsius water is converted to 100 degrees Celsius steam. So there are two processes. So another process is known as latent heat. So this is basically kind of first order phase transition. It's a first order phase transition. There where we have the two transitions. There is the discontinuity. We have the two transitions. One is where we have a temperature change, and another is temperature constant, but there is a change of the phase from water to steam. Now we want to see how QGP is converted in this in the hadron gas. If we don't know the whether it is only one step, it has two steps, like it has like here. If we don't know whether it is let's say there is only one step, first order phase transition, or zero, or it's a crossover, then we will do the wrong calculation at the level of quark and gluons. If we do the theoretical calculation by assuming crossover, then it will be wrong calculation. So this only we can use, this formula we are able to use because we know the first order phase transition, and it will match with the, if we do the experiment also for this particular case. So that is the importance of the QCD phase diagram. If we know the first order phase transition, then these types of calculation can be easily done at the level of quark and gluons, which give the precise results. So this is the importance of the QCD phase diagram. So thank you all. So if you like this video, please subscribe my channel. Okay, thank you.